Look up. Look out into the endless, silent theater of the cosmos. Our universe is filled with unimaginable beauty and violence. Brilliant stars burn for billions of years. Vast, cold voids stretch beyond comprehension. In the deepest, darkest corners of that cosmic ocean lie the most enigmatic objects we have ever conceived. The fabric of reality behaves there in ways that challenge our deepest understanding. These are black holes. They begin with a simple question: what lies within? What happens when you fall inside? A black hole is not a thing like a star or a planet. It is a place, a region of space-time where gravity has become overwhelmingly powerful, prevailing over every other force. Imagine a star many times the mass of our sun, shining for millions of years. Eventually, it exhausts its fuel. The outward push of fusion ceases and gravity takes over. In a final, catastrophic instant, the star collapses inward, crushing its matter toward an infinitely small, dense point. The result is a warp in space-time so profound that nothing, not even light, can escape. First, we must see the black hole from the outside. Every black hole is surrounded by a boundary, an invisible line drawn in the fabric of space itself. This line is not made of matter or energy. It is a purely gravitational concept. It is called the event horizon. Think of it as the edge of a waterfall in the river of space-time. Upstream, you can still turn your boat around and row away. But once you cross that edge, you are caught in the current, and there is only one direction you can go: down. The event horizon is precisely that, the point of no return. Once anything crosses it, whether it's a particle of dust, a spaceship, or a beam of light, it can never, ever get back out. To an observer watching from a safe distance, something very peculiar seems to happen as an object approaches the event horizon. According to Einstein's theory of relativity, intense gravity slows down time. So, from our perspective, a clock falling towards the black hole would appear to tick slower and slower. The light from that clock would become stretched and redder. Gravitational redshift. It would seem to take an infinite amount of time to actually reach the horizon, fading and reddening until it simply vanished from sight. We would never actually see it cross. It would seem frozen forever at the edge. But for the object doing the falling, the experience is entirely different. From its perspective, its own clock ticks normally. There is no dramatic barrier to smash through. For a truly gigantic, supermassive black hole, the crossing could be remarkably gentle. At the very center of the black hole, at the end of that one-way journey, lies the ultimate mystery. Our current laws of physics, the magnificent theory of general relativity, the strange world of quantum mechanics predict that all the matter that has ever fallen into the black hole, the entire mass of the original collapsed star, and everything it has consumed since is crushed into a point of zero volume and infinite density. This theoretical point is known as the gravitational singularity. It is a place where our mathematics breaks down, where our equations return answers of infinity, signaling we've reached the limit of our knowledge. The singularity is not just a very small, very dense object. It is a place where space as we know it ceases to exist, and time as we know it ceases to exist. General relativity says the curvature of space-time becomes infinite there. Gravity would become infinitely strong. Tidal forces would blow up. The stretching effect, the squeezing effect would become infinite. For any object approaching the singularity, the tidal forces would stretch it in one direction and squeeze it in others until it was torn apart into a stream of fundamental particles, a process gruesomely nicknamed spaghettification. This is the classical prediction for the heart of a black hole. But this picture is almost certainly incomplete. An infinitely dense point is a sign our theories need improvement. General relativity describes gravity and the large-scale structure of the universe. Quantum mechanics describes the bizarre world of atoms and particles. Both work perfectly in their domains, but they do not speak the same language. While we cannot send a probe past the event horizon and report back, we are not entirely without clues. The universe has provided us with natural experiments that allow us to test our ideas. We stand on the outside, looking in. What we see is beautiful and informative. The Event Horizon Telescope is a global network of radio dishes working in unison. It achieved something once thought impossible. It captured an image of a black hole's shadow. We saw a dark central region, the absence of light from beyond the event horizon, outlined by fiery, swirling plasma of the accretion disk. This confirmed Einstein's predictions. Another source of information is the sound of space-time itself. When two black holes spiral and merge, they create ripples in space-time, like waves from a stone in a pond. These are gravitational waves. Detectors like LIGO and Virgo can now hear these cosmic collisions. The waveform, especially the final chirp, provides a wealth of information, masses, spins, and confirmation that they follow general relativity up to merger. Observations have made black holes real and observable. We've found them in all sizes: stellar mass black holes, supermassive giants at galaxy centers. We see their influence in the frantic orbits of stars around Sagittarius A. Each observation adds another piece to the puzzle, yet every piece of evidence is from outside the event horizon. So, what happens when you cross the event horizon? The honest answer, the scientific answer, is that we do not definitively know. Our best theory, general relativity, gives us a clear but incomplete story. You travel on a one-way trip to the center, where you are crushed into the singularity, a point where space and time end. But this is almost certainly not the final word. The singularity is a signpost pointing towards a new, deeper physics that we have yet to discover. A theory of quantum gravity that will unite the very large, the very small, and we hope, resolve the paradox of the infinite. The quest to understand what lies inside a black hole is therefore one of the most important drivers in fundamental physics. It pushes us to reconcile our most successful theories and to imagine a universe even stranger and more wonderful than we currently believe. Could the information about what falls in be preserved on the event horizon? Could the singularity be a gateway to another part of our own universe, or to another universe entirely? These are the questions that keep physicists awake at night, questions born from the limits of our current understanding. This, in the end, is the true gift of the black hole. It is not just an object of immense gravitational power. It is an object of immense intellectual power. It represents a boundary, not just in space-time, but for human knowledge. It shows us where our brilliant theories reach their limits and where the next great revolution must begin.